All right, here we go. We're running. We're running. Okay, so let's take a look at the chapter. Ready? Listen up. Shh. Cliff, no touchy the hardware-y. Okay, listen up. Ready? Okay, we're going to do the exercises in 5.2 in a second, but let's see about this like preface here.
I thought you were going to show this on the screencast and it's like copyrighted.
That is true. You know, you're right. I didn't used to do that today. No, this is copyrighted. Yeah, I can't show this, can I?
It doesn't matter. They're not going to do anything.
Well, yeah, but wait, did I print it out? This is a copyrighted textbook. Yeah, that's a problem. Okay, you know what? You're right. I should print this out. Okay, file, print.
Just look at it on this computer. Look at it there. And
yeah, it's a little distant. I'll need a telescope. I need a camera for the screencast, a telescope to see that. You know, how much technology do we need?
Take one of the computers over there.
I know. Just drag them all here. I have like 500 computers on top of it.
Is that what you had in the other room? So you had the server?
I did, right. Yeah, I had the other one doing secret stuff we didn't see. All right, so I'm going to print it out. You also print it out. How long is it? Okay, YouTube, we're starting. What?
Back into those servers.
They claim they survived. So when they set up the room again, they'll bring them back. I don't know.
Tell them I want them for this room. Like we're not going back there anytime soon.
Yeah, I don't know where the hell they put them.
So call and say.
No, they're not going to do that. They put all that stuff away temporarily. That's open. They're not going to do it. I already asked, by the way. For a while.
Do you need to restart the screencast?
No, that's okay. All right, YouTube. I'm not going to display this textbook. Sorry, I can't do that. Boom. So let's talk. How about we get, all right, you guys are already in Sage, right? I'm going to get into Sage. All right, so we're in Chapter 5, Number Systems. Section 5.1 says, okay, follow along with your PDF. Go ahead. What is 5, mathematically speaking? There are many possible answers. 5 is how many fingers I have on my right hand. 5 is what follows 4. 5 is the property that all sets of 5 objects have in common. Do you realize there's a difference between number and numeral? There's a number 5 and a numeral 5. What's the difference? That's what he's getting at.
I don't know.
No? Anyone know the difference between the number 5 and the numeral 5? No? Number means how much. Numeral is a symbol you use to represent that how much. Right? Excuse me, are you guys paying attention or what? Yeah? Okay. So that symbol 5 that's printed on the page, that's the numeral. But when you think of 5 things, that's the number. How big it is, right? The numeral can be different depending on what base you're in. Haha, that's what this chapter is about. So we're going to talk about changing bases from binary to octal to hexadecimal to decimal. Why? Because the computer does this all the time. Okay? When you enter a problem, say you enter a problem in Sage. Wait, I got to log in. What do you mean it's not here?
This isn't close. You probably didn't create it.
I did create it.
Yeah, the joke is
No, it says username not in the system.
Sign in as admin and review the people that are there.
Maybe someone messed up his stuff. Maybe it was mine. You never know. Maybe it was mine.
All right, I'll be admin, whatever. All right, now, one other little thing about this, about your logins in Sage to protect your files, right? I wonder, is there some way to make it so that it doesn't go to this page when it starts up, that it goes straight to a login page? Is there? I'm not going to do that because it's messing up my login. But if you go into settings, is there some way to set it so that it goes straight to a login page so they can't get to admin and mess up your stuff?
Just click Manager Keys and see if you have the other account there.
It's gone. That's weird. I created 2 accounts yesterday and they both disappeared. No, not in Linux. No, that's really weird. All right, listen up. Shh. Is there a way to set this up so that it goes to the login screen automatically instead of the admin screen? There's got to be. So, because otherwise anyone can get to your stuff as admin, right? That's really weird. All right, I'm not going to bother with that. All right, I'm just going to use this, okay? So let me get rid of this stuff. And let's start from scratch. All right, so let's create. All right, so do you have the screen?
Yes.
Go to new worksheet. Okay? I'm going to call it, it's going to be, let's see, what, who, when, right? 5.2 number systems. Who is your name? When is today? 2012 dot, what the heck is it? 0116? Yes? Okay. All right, so if you print this out, it's got your name, it's got the topic, it's got the date we started working on it, okay? All right, so first things first. I'm not actually doing any exercises yet. I'm just talking about... Huh? Oh, okay, there's more than one way to skin a cat. Yes, of course. 2013. Okay, everybody's a critic. All righty. So if you type 5 and you hit evaluate, you get 5, right? Amazing. But that's 5 in base 10. If I tell it to do 5 plus 2, evaluate, I get 7. Now what just happened? You're entering the problem in base 10, and you're, Cliff, what's going on? And you're getting the answer out in base 10, right? But the computer doesn't know how to do stuff in base 10. At the chip level, it's optimized for binary arithmetic. What does that mean? Base 2. So it physically takes the 5, converts it to base 2, takes the 2, converts it to base 2, adds them up, gets a base 2 answer, and then converts it back to base 10 to talk to display the answer to the dumb human. Dumb human. Why can't we just enter everything in base 2 to begin with, you know? Why? Because the computer is very fast and very accurate in base 2. Now, let's say you wanted to save this information to a file. The computer doesn't save this stuff as in base 10 either. It saves it in base 16, hexadecimal. Why? Right. It takes a smaller amount of space on the hard drive to represent larger numbers. So it converts everything to hexadecimal when you save it to a file. So the computer is always converting to and from base 10 and base 2, to and from base 10 and base 16, to and from base 2 and base 16 all the time, behind the scenes, at the chip level. We have to understand how that works. That's what this is. Do you know how to write 5 in binary? How does that work? Anyone know? Let's talk about this. Let's see. Let's say I want to... Do I have a pen? Give me a pen. How about a red pen? All right, so I want to know what 5 in base 10 equals as a base 2 number. Okay, now the computer, our computer, is a 64-bit computer. So it converts everything to 64 bits. What does that mean? What is a bit? Does anyone know? I'll tell you this much. It's the smallest piece of memory the computer can talk about, or the smallest piece of information, the smallest number. Do you know what that is? A bit is just a nickname for a binary digit, one place in binary. Okay? Now, binary is base 10. Do you know what that means? That means what digits are you allowed? Base 2, sorry, I said it wrong. Binary is base 2. That means you have only 2 digits. What are they? 0 and 1. Okay. Binary is base 2. That means the placeholders aren't powers of 10 either. If you were talking about a base 10 number, like 165. Well, I can't write. Wait, go away. I got to get used to this thing. 165 in decimal means 5 in the what's place? 1. 6 in the tens and 1 in the hundreds. But if I'm talking about a binary number like 1101, I'm talking about a 1 in the ones place, a 0 in the twos place, a 1 in the fours place, a 1 in the, not 16, you're too far, eights place, it's powers of 2, so multiply by 2 every time. So ones times 2 is, ones times 10 is tens, times 10 is hundreds, okay. 1 times 2's is 2, times 2's is 4, times 2's is 8. So what is this number? This is a binary number, base 2. Can you tell me what it is in decimal? Ugh. I'm not used to this tablet anymore. I used to use this all the time, nice and neat. I want to convert this to a base 10 number, decimal. Well, you just told me you have 1 in the ones, no 2's, 1 in the 4's, and 1 in the 8's. So 8 plus 4 is 12 plus, well, plus 0 plus 1 is 13. These are two different numerals for the same amount. Now, if I told you I had 13 bananas, you could visualize that, right? You can see that there's a, is it a lot? Well, it's a lot for bananas because they're big, I guess. But it's not really that much, right? I mean, you can visualize that. But if I told you you have 101 binary bananas, God knows what the heck that is. That's unless you convert it, right? Because you're familiar with base 10. So 13 in decimal and 1101 binary are two different numerals for the same number. Two different numerals for the same amount. Do you see the difference between numeral and number now? Yes? No? This numeral, symbol, means the same as this numeral or symbol. That's what numeral is. It's a symbol that represents the number. They represent the same number. They represent the same amount. Right? Okay, so with that said, how do you write 5 in base 10? Base 2.
1, 0, 101.
Now remember, we have ones, zeros, ones, twos, 4's, and 8's, all right?
101.
101, right. Let me go through it. Do you need any 8's?
No.
No. Do you need any 4's?
Yeah.
Yes. What's left? If you used up 4, what's left? 1. Do you need any 2's? No. Do you need any 1's? That's how you do it. Okay, so now we have two different numerals for the same amount, meaning 5 things, right? 5 in base 10 or 101 in base 2. Now, I arbitrarily made it a 4-digit number. It doesn't have to be. And this one digit in binary, that's nicknamed a bit. You ever hear of bits and bytes? Right? That's a bit, the smallest piece of information that your computer can process. Okay? What's a byte? It's how many bits? No, it's not that many. It's only 8. It's the minimum number of bits you need to represent all the keys on your keyboard. Now don't forget, you have two keyboards. You have the keyboard in front of you, which can have as many as 128 different keys. And there's the upper half ASCII code for a whole bunch of weird symbols like, I don't know, like the cent sign for dollars and cents. Like the pound symbol for pounds sterling in Britain. Like the curses that Ryan does. What am I talking about? That thing that, which one did the curses? The latest fancy print? Fancy print 5. If you look up version 5 on eBay, it's $1,000 right now. Aren't you selling it? It's up minimum bid $1,000 now, right? Okay. His fancy print, the last one, put sort of like these frames around everything. And that's what's called half-assed graphics, using weird symbols to sort of look like graphical designs, right? The very first version of Windows, no, before the first version of, there was a version of Windows 1, which was testing, beta, right? The first commercial version of Windows 2.0 didn't catch on. Around the same time, a company called GeoWorks made their own version of Windows. But it was all based on half-ASCII graphics. So when you had pull-down windows, they all had like these weird frames, text frames and stuff. It was really weird. But it worked. It was sort of like Windows, right? Then Windows 3.0 took off. And then GeoWorks went away. But anyway. All right, so that's what this chapter is about. All right, so let's see. Let's see. I'm just going to go through. I'm on page 78. Anything interesting on page 78? Okay, page 78 talks about 21 base 3. Okay, let's do that. What is 21 base 3? Let's see. Let me expand this. Let me pull this down a little bit. Okay, so now you can answer this question. I'm on page 78. Do you see in the middle they're talking about 21 base 3? Do you see it? Are you on page 78? Okay, in 5.2? Okay. What is 21 base 3? Can you convert that to base 10, let's say? Base 3 is alternately known as trinary or ternary. People can't decide what to call it. Like binary, trinary, but a lot of people call it ternary. I don't know why. And this is base 10 decimal. So you could write the number of the base or put the little abbreviation like bin for base 2, dec for base 10, tri for base 3, right? Can you convert that for me? The 1 is in the what's place. It always starts with the 1's place. The 2 is in the 3's place, right? Because it's base 3. 1's place, 3's place. What would be the next place? 9's place, 27's place, right? Okay, so I have 1, 1, and 2, 3's. So how much is that? 7. Is this terrible? No, it's not. Do you see that middle paragraph in the middle of page 78? It says 21 base 3 would mean 2 3's plus a 1 is 7 base 10. Do you see it? All right. Now, it says 14 would become 112. Oh, okay. Now they're asking, can you convert 14 from base 10 to base 3? All right. Let's see if we can do that. What's 14 base 10 as a base 3 number? That's a weird 4. Okay. All right. Now remember, you know the places. There's 1's, there's 3's, there's what? 9's. Okay, what's the next one? 27 is too big. I don't need that, right? So for 14, does 9 fit? How many times? Once. Okay, so take 1 9. Take the 9 out, what's left? 5, actually. Yeah. All right, now this is the what's place? 3. How many times is 3 going to 5 at most? Once, remainder? 2. How many ones do you want? Is that what he said? 14 would become 112. Is this okay? It's not that hard to convert to and from decimal, right? To convert to decimal, you just look at the placeholders. 1, 1, 2, 3's. To convert from decimals, you're sort of dividing. 9 goes in once, remainder 5. 3 goes in once into 5, remainder 2. 1 goes into 2, twice even, done. So when you're converting from decimal, you're dividing. When you're converting to decimal, you're multiplying. You're looking at the placeholders. 1 times the 1's place, 2 times the 3 place, something times the 9's place, whatever, right? Okay, is this terrible? Not really. All righty. So now, go to page 79. Page 79 says, what's 2,211? Now, if you say it like that, it sounds like you're talking about a normal base 10 number. So people don't do that. They say 2211, right? Just to make the point that we're not in base 10. All right, we're not in Kansas anymore, Dorothy. Right? Okay. So 221 base 3 and 102 base 3. Can you add it up? Now, let me remind you, in base 3, we have how many digits? 0, 1, and 2, right? Do you see that there are only 0s, 1s, and 2s in here, right? Okay, so go ahead, add it up. What is 2 plus 1? Since, be careful, 2 is the biggest digit. So when you run out of digits, don't you carry? So 2 plus 1 is 10, carry the 1. What? Because 2 plus 1 is usually 3, right? But isn't 10 in base 3 the same as 3 in base 10? Nothing in the 1's place, so 1 in the 3's place? No matter what system you're in, when you borrow, when you're subtracting, or carry when you're adding, you're always carrying or borrowing 10. But 10 means the base. So I'm carrying 10, but it means 3, right? So it's 1 plus 1? 2. We got a 2, numeral. Sorry, we have a 2-digit, I should say. 2 plus 1? 10, carry the 1. 2 plus 1? 10, carry the 1. Done. Now, this isn't as weird as it looks. Remember Gracie? Remember Grace Murray Hopper? She was working on the Harvard Mark I, a vacuum tube-based machine, not a chip-based machine. Our machines, chip-based, use binary. Vacuum tube-based computers used ternary. She was doing this kind of stuff all day long. until it was coming out of her ears. The arithmetic that that computer did was base 3 arithmetic, like ours is base 2. All right, let's leave it at that. Okay, so I'm going to turn this off. Not this. This. Okay, I'm turning off my recording. Bye-bye, YouTube.